Hello again, everyone. In this video, we will discuss forces and using Newton's second law of motion to do calculations. This makes up a rather large part of the problem solving in Physics 151 going forward, so it's going to be important to take the time to understand it early. One thing to note is that force is a vector, so it has both a magnitude and direction. This also means that forces add as vectors or by components, which we have discussed earlier. This addition of forces as vectors is a key aspect in how we solve force problems. Forces have many different sources that they can originate from, but in simple terms, they are something that push or pull objects, affecting their motion. The standard unit for a force is newtons, which is a combination of the units kilogram times meters per second squared. It is in Newton's second law of motion that we relate how forces affect motion. The law states that the net force acting on an object is equal to the mass of the object multiplied by its resulting acceleration. This net force is the term we use for the sum or combination of all the forces that we are considering acting on an object, given by the summation notation here. Since this is what we mean by net force, according to Newton's second law of motion, this must be equal to the mass times acceleration. So to construct our net force equations, we will consider all forces acting on an object and add them up on one side as vectors. Then on the other side of our equal sign will be our mass times the acceleration of the object in that component direction. If we are dealing with a problem that has two or more dimensions, we must make separate equations for each component direction. That is, we will add up all the x direction forces to get the mass times the x direction acceleration, and then separately make an equation for the y direction. Let's do a one-dimensional example to get us started. A person with mass of 70 kilograms is standing in an elevator. Find the person's apparent weight if A, the elevator accelerates upwards at 2 meters per second squared, and part B, the elevator is accelerating downwards at 2 meters per second squared. Looking through this problem, we have a mass of 70 kilograms, and for each part we have an acceleration of 2 meters per second squared. But what exactly is the question asking for when they say apparent weight? Whenever you see this phrase, relate it back to the normal force. What we mean by apparent weight is how much the surface feels like it has to push back with to keep you or the object falling or passing through the surface, which is exactly what the normal force is. Now that we know we are looking for a specific force, we might want to start this problem with a free body diagram. This is where we draw all the forces that are acting on an object or a person so that we can keep track of what forces are present and also which direction they are pointing in. I'll go ahead and sketch out my person standing in an elevator here. And now I want to ask myself what forces are acting on this person. And for each force I will draw an arrow pointing in what direction that force should be going in. In many problems in this class, the implication is that we are on Earth, which if that is the case, our person here will experience gravity pulling them downwards, since the force of gravity is always vertically down to Earth. I could label this a few different ways, Fg for the force of gravity. This is also defined as the weight of the person, both of which I know should just be equal to m times g, since we are on Earth. What other forces should be present here? Well, I know the person is standing on the floor of the elevator. The floor is a surface that is holding the person up. Therefore, I should expect that surface to exert a normal force, which to keep the person from just falling through the floor must push perpendicularly upwards. The normal force always points perpendicular away from the surface. For this scenario, we have now drawn all the relevant forces that are acting on this person. But while we're at it, we do have a little bit of information on which direction this elevator will accelerate in, which could be drawn in our diagram here. I will use a different color of arrow to not confuse it with the forces I've already drawn. But for part A, we have an upwards acceleration of 2 meters per second squared. Keeping track of which direction your acceleration is with arrows like these could be important for problems like this, but you do want to make sure that you don't confuse any arrows you draw for the motion with actual force arrows, which is why I've color-coded the forces are red while the motion is black arrows. Once we've drawn our free body diagram, and we've made sure everything is broken up into the components that we would need to use in our calculations, we are ready to make our net force equations using Newton's second law. For this problem, everything is in the y directions, either straight up or straight down. So all I have to worry about in this problem is making a net y force equation. Now when I go to add up all my forces on the left side of this equation, I want to make sure that I'm adding things up as vectors. So I have to think about in my y direction, which is the positive direction and which is the negative direction. Typically, the convention is anything upwards is positive and downwards is negative. So when I go to add up all my forces, the normal force is upwards, so I'll leave that as a positive normal force. But the force of gravity, the weight of this object, is downwards, which means when I go to add it to the normal force, since it is in the opposite direction, it should get a negative, so minus mg. And since these are the only forces I have to add, this should be equal to whatever the mass times the acceleration of this object in the y direction is. So here's my net force equation, which means I can start plugging things in and see if I can solve for what I'm looking for. In this case, the normal force is my unknown, so I'll leave that as n, minus the mass, which is 70 kilograms, times the acceleration due to gravity, which on Earth is 9.8 meters per second squared, equals the mass, which again, 70 kilograms, now times the acceleration of this object, which remember, acceleration is also a vector, so when you go to plug in an acceleration, keep in mind which direction it is going in. For part A here, the acceleration is upwards, and I have chosen upwards as positive, so for this case, I should plug in positive 2 meters per second squared. Going through and doing some of these calculations, I get the normal force minus 686 kilogram meters per second squared equals 140 kilogram times meters per second squared. And adding 686 to both sides will get me to the normal force, which I find to be 826 kilogram meter per second squared, which is a Newton. Therefore, the apparent weight, which is the normal force, is this 826 newtons. Now that is for part A, so what changes in part B? Well, for part B, it's mostly the same scenario. Our person is still in the same elevator, however, the elevator is accelerating downwards now, so in our diagram, the acceleration is downwards. Since we have all the same forces, our net force equation still looks the exact same, so we can jump right to where we have the normal force minus mg equals mass times acceleration. However, this time, let's see what happens when we plug things in. The normal force, that's what we're looking for, minus the mass, which is 70 kilograms, times gravity, which is 9.8, has to equal the mass times the acceleration. But this time, since the acceleration is downwards, when we go to plug in that 2 meters per second that the problem gave us, we have to remember that we chose downwards is the negative direction. So to properly handle this, we plug in a negative 2 meters per second squared. Doing some of the calculations, we get normal force minus 686 newtons has to now be equal to minus or negative 140 newtons. So when we add 686 this time, we get that the normal force is only 546 newtons. So we can see that the apparent weight of this person, the force that feels like the floor has to push back on them, does change depending on which direction the elevator is accelerating in. Let's see what a slightly more complex force problem might look like. We have a person pushing a box that has a mass of 20 kilograms with a force of 50 newtons at an angle of 20 degrees below the horizontal. If the box moves with a constant velocity across a horizontal floor, what is the coefficient of kinetic friction between the box and the floor? There are clearly going to be multiple forces involved in this problem, so sketching out a diagram might be where we want to start. Now this problem doesn't really specify what direction we are moving the box, so I'll just choose that it's moving to the right and handle things as appropriate from that choice. So here's our floor with the box moving across it. We know this box has a mass of 20 kilograms. I could go ahead and write that here. The problem does give us what force we are pushing this box with. So assuming I'm pushing it towards the right, I am pushing the box slightly at an angle here. They tell me 20 degrees below the horizontal. So if I draw a force that is generally to the right, but at an angle, I've drawn it downward since I'm below the horizontal at this angle of 20 degrees. So that's the force I know I'm pushing this box with. What about any other forces that could be happening here? Just like before, presumably we're on Earth, so I'll have the force of gravity, or the weight of this box, going directly vertically downwards. I know this should always be equal to mg. The box is on the floor, which is a surface that will push back against it to keep it from just falling through the ground. So there will be a normal force directly away from that floor. And for this problem, I am now considering friction. Keep in mind that a frictional force is something that always opposes motion. So if this object is now moving to the right, as I initially suggested, the frictional force must be opposing that rightward motion, which means friction must be going directly to the left. One of the complications with friction is that there are actually two types to consider. There is static friction for an object at rest, but kinetic friction for an object in motion. In this case, since the object is moving across the surface, we will be experiencing kinetic friction. And with that, we have drawn all the forces that we would consider for this object, as well as the direction of motion. So let's start thinking about what we are looking for and how we might get to it. In this case, we are looking for the coefficient of kinetic friction, which is given by this symbol mu subscript k. In this class, the only equation we see this symbol pop up in is in the kinetic friction equation, which tells us that the magnitude of kinetic friction is given by the coefficient multiplied by the normal force. So if we're trying to solve for the coefficient using this equation, the first thing we need to know is the force of friction and the normal force. Since we need both of those forces but don't currently have any numbers for them, it seems that we will have to go through and make our net force equations using Newton's second law. In this example, we have both horizontal and vertical forces to keep track of, so we will be making separate equations for both the x and y directions. Before we can do that, however, we might want to break everything down into their x and y components if they aren't already purely in those directions. In this case, the only force that we need to break down is our pushing force of 50 newtons. That is the only one that's at an angle and not purely in the x or y direction. Our pushing force is down and to the right, which means we'll have a horizontal component that is to the right and a vertical component that is downwards. This creates our right triangle, which we can break up using SOHCAHTOA. The magnitude of the x component will be the adjacent side, which means we pick up 50 times the cosine of that 20 degrees. Meanwhile, the y, or vertical component, is the opposite side to this angle, so its magnitude will be given by 50 times sine of 20 degrees. Now with everything broken down into components, I can start making a separate net force equation for my x and y directions. For my x direction equation, what forces are acting in that x direction, so either left or right? I will choose the convention that going to the right is positive and going to the left is negative. So my pushing force has a rightward component, so that will be positive 50 cosine of 20. Meanwhile, the only other horizontal force is the friction going to the left, so I'll have minus the force of friction must be equal to the mass times the acceleration in the x direction. Now let's think about this. Do we have an acceleration in this problem? We don't have a number from the word problem. However, keep in mind that this box is moving at a constant velocity. Whenever we have a constant velocity, that means that our acceleration is equal to 0. So we could go ahead and plug in acceleration in the x direction is 0. Meanwhile, what does our y direction equation look like? When we're adding up our forces, we're considering what is going up or down, up as positive again and down as negative. In this case, normal force upward, so positive in. We have the vertical downward component of our pushing force, so minus 50 sine 20 degrees. And we also have the weight or force of gravity going directly downwards as well. So minus mg must be equal to the mass times acceleration. But this object is not going to be moving up or down at all. So it has a constant vertical velocity of 0, which means acceleration is also 0. So the right side of this equation would also be 0. If we take a look at what we have here and start trying to plug things in, let's see if we can start solving for some of our unknowns. In our x direction equation, we see that 50 times cosine of 20 degrees minus whatever the force of friction is must be equal to 0. So moving things around, we see that the kinetic force of friction must be equal to that 50 cosine of 20 degrees. So there is one of our unknowns that will help us ultimately solve this problem. Now what can we find from the y equation? Well, the normal force is our only unknown here, minus 50 times sine of 20 degrees, minus m times g, we know what goes into those. The mass of this box is 20, gravity is 9.8, and it all has to add up to 0. The 20 kilograms times 9.8 will give us 196 newtons. So moving everything around to solve for our only unknown, which is the normal force, will tell us that normal force equals positive 50 times sine of 20 plus that 196. We can now calculate both the normal force and frictional force, which means those can now be plugged in to solve for our coefficient of friction. So again, that equation says force of kinetic friction equals the coefficient which we're looking for times normal force. So plugging things into that will give us 50 cosine of 20 degrees has to equal that kinetic coefficient multiplied by the normal force, which is 50 sine 20 degrees plus 196. To solve for the coefficient of kinetic friction, we would need to divide by that whole parentheses. So 50 cosine 20 degrees divided by that 50 sine 20 plus 196, and we can calculate what that would give us. In this case, we find that the coefficient of kinetic friction is about 0.22. And these coefficients of frictions have no units. That concludes this video on forces, but I definitely recommend getting as much practice with these as possible.